All right, hi Mr. McLean. I hope you're doing good. Here's my video for the thermochemistry test. Okay, so the first question gives us the chart with different substances and their specific heats, and the question is, if the same amount of heat is supplied to 10 grams of each substance, all at 21 degrees Celsius, which substance would reach the highest temperature? The answer is silver, because it has the smallest specific heat of the 5 different substances, and this means that it would take less energy to heat it up, which means it would heat up much faster. So it is silver. And then the second question, it gives us this reaction right here, and it says 10 milliliters of 0.5 molar hydrochloric acid and 10 milliliters of 0.5 molar sodium hydroxide are mixed together. And it gives us the initial temp and the final temp, which are 23.2 degrees Celsius and 26.7 degrees Celsius. And the question is the reaction exothermic or endothermic? And we know that it is exothermic because the temperature is increasing, which means that heat is going out of the reaction. So that is not really super hard. But the next question is when the HCl and the NaOH solutions are mixed, how much heat is generated in joules? And it gives us the specific heat, which is 4.18 joules per gram degrees Celsius. So we know that if we're trying to find the heat, we're going to use the equation Q equals mc delta T. And to find that, we have to have the mass, and we know that each of these, from the earlier problem, it told us that they're each 10 milliliters, and 1 milliliter is equal to 1 gram, so we know that there's going to be 20 grams of solution when they're mixed together. And then it gives us the specific heat, which is 4.18 joule per gram degrees Celsius. And then the temperatures it gave also in the earlier problem, which is 26.7 minus 23.2, because you're going to subtract the final temperature from the initial temperature. So then when you do, when you subtract the temperatures, you're going to get 3.5 degrees Celsius. And then when you put 20 times 4.18 times 3.5 in your calculator, you get that the heat that is generated is 292.6 joules. But you know that it's negative because it is exothermic, and it is like the heat is coming out of the reaction. So we know that this is going to be negative, even though you don't get a negative answer from the equation. And then for the next question, what is the molar enthalpy of the reaction in kilojoules per mole? So we know that we're going to be using 2 different equations. The enthalpy of the reaction equals Q over the number of moles of the reactant, and then the molar equals moles divided by volume in liters. And you're going to be using this equation to put in the bottom here. And we already have the Q from the earlier problem, but this has to be in kilojoules. So you're going to do negative 292.6 joules, and then you're going to do stoichiometry to find it in kilojoules. So there's 1,000 joules in 1 kilojoule, and this equals negative 0.2926 kilojoules. And then to find the number of moles, we know that we have 0.5 moles equals, or 0.5 molar, and then we don't know how many moles we have of this solution, and you're going to divide that by 0.01 liters, and you're pretty much going to cross multiply, and you're going to get the number of moles, X equals 0.005 moles. So then you can take these two numbers and put them into this. So your enthalpy of the reaction equals negative 0.005 2926 kilojoules divided by 0.005 mole, and the change in heat, or the enthalpy of the reaction, I mean, is negative 58.52 kilojoules per mole. So then for the next question, 100 kilojoules of energy is measured to come out of the reaction in another trial of the experiment. How many grams of water would be produced if that much energy is generated? So we're also going to have to do stoichiometry here as well. And you're going to start off with your 100 kilojoules. And you're going to divide it by the number that we just got in the previous question. So negative 58.52 kilojoules per mole. Oops. And then you're going, on top here is going to be 1 mole of the reaction, because this is how many moles is in the reaction. Or in 1 mole of the reaction, there is negative 58.52 kilojoules per mole. And then we're going to come down here and do 1 mole of reaction as well, so that those will cancel out, those units. And then in 1 mole of the reaction, there's 1 mole of H2O, and we got that from the equation that was given to us. So 1 mole of H2O, and then we're also going to put 1 mole of H2O down here to also cancel out the moles, and we're going to put it into grams because it's asking for grams. So it's going to be 18.02 grams of H2O, and that is equal, when you put it into your calculator, to 30.79 grams. Okay, next question. So the heat of fusion of pure water is about 6 kilojoules per mole, and the heat of vaporization is about 41 kilojoules per mole. So for the reaction, how would the heat of fusion and vaporization be different from pure water? Would they increase or decrease? So when it's not pure water and when other substances are added in, it's going, for heat of fusion, it's going to need to be a lot colder to freeze the substance. And for heat of vaporization, it's going to be a lot hotter for it to actually completely vaporize. So both of them are going to increase for them to vaporize and freeze. And then I messed up the first time when I did this. So here is the phase diagram for water. So right here, the intermolecular forces are forces which mediate interaction between molecules, and the forces of attraction and repulsion act between the molecules, and that also plays a part in the phase, like this phase diagram. So point A here is the triple point between like solid, liquid, and gas, and at the triple point it's just a cycle of all the phases, so it's constantly going between the 3 phases between solid, liquids, and gases. And then B is the normal freezing point when it's pure water, C is the normal boiling point when it's pure water, and then E is the critical point, and that is when the pressure and the temperature are so high, like as you can tell, it's at the very end of the graph, that you can't tell if it's in the liquid or the gas phase. So over here, this is like the solids, this is the liquids, and these are the gases. And it shows like the temperatures, and this does not have a label, but this is supposed to be temperature in degrees Celsius. And that's it. I hope you are doing okay and enjoying time at home with your family.